So guys, welcome back. So today we talk about Toeplitz matrices and shift invariant filters. So this is the outline of the lecture. I'll talk about Toeplitz matrices, the basic ideas. I'll talk about pass multiplication by the FFT and low pass filters. So first of all, as an introduction, what is a Toeplitz matrix? It has constant diagonals, where the first row and column would tell you the rest of the matrix, because in fact they contain the first entry of every diagonal. In fact, what we've seen before, we've seen circulant matrices, as you recall. In fact, they are Toeplitz matrices that satisfy the extra wraparound condition that makes them periodic, in fact. So effectively, C3 is the same as C1 in circulant matrices, okay? So this is a Toeplitz matrix, as you see. So it is enough to see the components of the first column and the first row to conclude about the remaining components of the matrix. So you see this upper diagonal is all filled with A minus 1. Similarly, A minus 2. And similarly, A3. Okay? And you can see that this lower diagonal is all filled with A1s, A2s, and A3. And the whole diagonal, main diagonal, is all filled with C0s. On the other side, you have a circulant matrix, which, as you recall, here this is a circulant matrix of size 4. So you see that the C3, the remaining component, comes back here at the lower bottom element. Okay? So in fact, circulant matrices are Toeplitz matrices, but they satisfy this extra wraparound condition that they are periodic. In fact, you have kind of a period. So in fact, circulant matrices are considered to be perfect for the discrete Fourier transform, because they do always have this property that CD equals DC. So if you multiply two circulant matrices, CD and DC, CD, you always have this kind of commutativity condition for the multiplication. And their eigenvectors are exactly, in fact, as you've seen before, the columns of the Fourier matrix, as we've seen in section 4.2. Now, their eigenvalues for the Toeplitz matrices, in fact, they are the values given by C theta, which is the sum of CK times E to the power ik theta at the n equally spaced angles, theta, which is given by 0 to pi over n, 4 pi over n, as you've seen with the Fourier matrix. Toeplitz matrices are nearly perfect, not as much as circulant matrices, because they are these matrices we use. In fact, we use them in signal processing and in convolutional neural nets. If we have the time, we'll come back to it. So Toeplitz matrices are quite important for convolutional neural network. They don't wrap around as circulant matrices. So in fact, the analysis of a Toeplitz matrix is based on the two-sided polynomial we can obtain. This is the polynomial, we can call it. So from now on, we call that, we are talking about the polynomial A theta with coefficients obtained from the entries in the first row and the first column in the matrix, A1 minus n, A0, till you reach AN minus 1. And in fact, these provide what we call a frequency response, or the symbol of A theta is given as follows. Okay, this is the sum of AK by e to the power ik theta. So now for this polynomial, it's real when A, so the Toeplitz matrix, is symmetric. In that case, we do have the following, that AK times e to the power ik theta plus AK times e to the power minus ik theta is in fact equal to 2 times AK cosine k theta. So what happened here, the imaginary part disappeared, okay? Because in fact, you just added kind of two conjugate numbers. So C of theta is non-zero when C is invertible. here we come back to circulant matrices. And the symbol for c to the power minus 1 is 1 over c theta. So, but for Toeplitz matrices, using that fact, so using that a theta is not 0, is not correct as a test for invertibility. And in general, A inverse is not Toeplitz, except for triangular matrices. This is an exception. Circulant matrices, C, they do provide what we call before, as you've seen, cyclic convolution. But Toeplitz matrices, there are no non-cyclic convolutions, because you can see that the coefficient A, if you put them in kind of a vector A, followed by projection, you obtain what we have on the X space, AX convolve A star X, then it keeps the components 0 to n minus 1. And on the 0 space, the projection, A times x of theta, it multiplies A theta by x theta, then projects back to n coefficients. So what we want to use, we want to use the simple polynomial A theta to learn about the Toeplitz matrix. In many problems, in fact, the Toeplitz matrix is banded, and the matrix only has W diagonals above and below the main diagonal. So this is an example of a banded Toeplitz matrix. So you see kind of a band which is wrapping around the main diagonal, and all the remaining elements here are 0. Okay, so in this tridiagonal Toeplitz matrix, only the coefficients from A minus W to A W can be non-zeros. And what we call the bandwidth is W, with a total of 2W plus 1 non-zero diagonals. Okay, you see already the fact that we're using this kind of terminology, it is brought from signal processing. And this is an example of what we call tridiagonal Toeplitz bandwidth with W equals 1. And you see, you can just know A0, A1, and A minus 1 to know exactly the structure of A. So what do we understand from that? We do understand that tridiagonal Toeplitz matrices and their eigenvalues for large size n, by studying the symbol A theta, which is the polynomial given by these coefficients. So it's A minus 1 times e to the power minus I theta plus A0 plus A1 times e to the power I theta. And in fact, it is strictly built from A minus 1, A0, A1. Okay? So as an introduction now to the basics, the basic ideas we're going to use for the filters. So in signal processing, in fact, these kind of Toeplitz matrices, they do provide what we call a filter. And the matrix multiplication AX in the time domain, in fact, translates into ordinary multiplication in the frequency domain. Okay, so we do have A theta, X theta in the frequency domain. That is the fundamental idea, but it's not, in fact, exactly true. So the Toeplitz theory is, in fact, on the edge of simple Fourier analysis, one frequency at a time, but with kind of boundary interference. So, for example, a finite length signal, which is given by x0, xn, has boundaries at 0 and n. And those boundaries, in fact, they do strive a simple response to each separate frequency. And a Toeplitz matrix essentially produces what we call a convolution. We've seen already what is a convolution. So the main word here, my topic, we always use in data science. So if you want what we call a band pass filter or a low pass filter that preserves frequency, where theta is between A and B, and removes all other frequencies, then we'd like to construct A theta to be near 1 in that band and near 0 outside the band. Again, an ideal filter with A exactly 1 and 0 is in fact impossible until your n goes to infinity. So what do we have? We have linear finite difference equations with constant coefficients that produce Toeplitz matrices. This is kind of a little bit, let's say, complicated to detail, but we'll see just a small example. The equations don't change as the time goes forward, so it's linear time invariant, and they don't change in space. So we do have what we call linear shift invariant, the LSI. Now let's see an example, a couple of examples. So for example, the familiar -1, 2, -1 second difference matrix is in fact an important example of tridiagonal Toeplitz matrix. So you have -1, 2, -1. These, in fact, guys, they do replace what we've seen in the previous slide as A-1, A0, A1. Okay. So the polynomial you obtain, A theta, would be given by -1 e to the power minus I theta plus 2 -1 times e to the power I theta, which is in fact real. Why is it real? Because this matrix, this tridiagonal matrix, is going to be symmetric too. And the fact that this I theta is always going to be positive. Why is it going to be positive? Because cosine theta cannot be larger than 1. Tells us that A is symmetric, positive, semi-definite, or definite. And the fact that A is equal to 0 when cosine equals 1, which means when theta equals 0, tells us that, in fact, the lambda m, in fact, in A will approach 0 as n increases. So the finite Toeplitz matrix A is barely positive definite, and the infinite Toeplitz matrix is singular, all because the symbol A theta is equal to 0 when theta equals to 0. Now let's see what happens with the inverse of a Toeplitz matrix A, which we said usually is not Toeplitz. For example, if you consider this, the inverse of this matrix, which is Toeplitz, you see you have 2 -1 -1 0 0. You have the Toeplitz structure, okay? And more than that, you can say that this is a tridiagonal Toeplitz matrix. Now, if you try to invert it, you're going to have this matrix, which is not Toeplitz. Okay? You see why? For the simple reason that you see the items in the main diagonal are not the same. Okay? So this breaks the whole idea that inverses of Toeplitz matrices are also Toeplitz matrices. Now we'll talk about what we call aliasing. So for tridiagonal matrices, we don't need, in fact, a special algorithm to multiply AX. In fact, this requires what we call 3n separate multiplication because of this very specific and very easy structure of tridiagonal matrices. But for all full dense matrices, the Toeplitz and circulant properties allow, in fact, a major speed up in the theta space by using what we called before the fast Fourier transform. What we will have, this applies. What we'll have is that what we should recall is that circulant matrices are cyclic convolutions, and in the theta space, the matrix vector multiplication Cx becomes the following, okay, which is the product of these two kind of large sums, and this product will in fact give powers of e to the power theta that go outside the range from k equal to 0 to k equals n-1. And those higher frequencies and negative frequencies are what we call aliases of standard frequencies. In fact, they are equal at every theta, which is equal to p times 2 pi over n. So what is aliasing? In fact, e to the power I n theta is equal to 1, and e to the power n plus 1 theta is equal to e to the power I theta, and e to the power I times n plus p theta is equal to e to the power I p. Okay, so you have it repeats. It's in fact it repeats this. It reflects this periodicity. So Now let's talk a little bit about this process of fast multiplication by FFT to save the time. So cyclic convolution, as you've seen before, brings every term of this product back to a term which is between 0 and n. So in fact, circulant multiplication Cx needs only in fact a complexity about n log base 2 n steps because of convolution by the fast Fourier transform. Now, cyclic convolution Cx and Cd give the entries of Cx and Cd, and a Toeplitz matrix multiplication Ax is not cyclic. Why? Because we said that Toeplitz matrices are not non-cyclic convolutions. So higher frequencies in A theta x theta don't fall back perfectly into lower frequencies, but we can use cyclic multiplication and a circulant by a doubling trick, which embed A into a circulant matrix. So this A, which is a Toeplitz matrix, will be embedded into what we call a circulant matrix. The structure we obtain is a kind of complicated. So this is the Toeplitz matrix. But once embedded into a circulant matrix, we have a very large circulant matrix of size 2n-1. Okay, but what we are sure about is that this is going to be a circulant matrix, which means we can use the properties of cyclic convolution. Now, to compute this Ax of size n, we can use the circulant matrix obtained, which is defined as follows, of size 2n plus 1 to n plus 1, I guess. 2n plus 1, not 2n minus 1. And the process, in fact, works this way. You add n minus 1 zeros to extend x to vector x of size 2n plus 1, and multiply Cx using the fast Fourier transforms by cyclic convolution. Then the first n components of Cx produce the desired Ax. Okay? Now, the last part of the content of the slides is about what we call the low-pass filters. So, in fact, what is a filter? It is a convolution, and it is obtained by a multiplication by Toeplitz matrix. So, in fact, going through a low-pass filter, the constant vector, if you see this is a constant vector, which is all at once, can come out unchanged, such that if you multiply by the Toeplitz matrix A, you obtain back X. But an oscillating high frequency signal of the following kind, where you have 1 minus 1, 1 minus 1 minus 1, has A times Y, which is approximately equal to 0. Okay? Those are the outputs if A0 is equal to, in fact, the sum of the AKs, which is equal to 1, and A of pi is almost 0. So here is a low-pass example. Okay, so AXN will give you 1 over 4 AX minus 1, plus 1 over 2 XN plus 1 over 4 XN minus 1. And that Toeplitz matrix A is symmetric. It is symmetric. Its three diagonals have entries 1, 4, 2 over 4, and 1 over 4, which means this is the structure of the matrix we're talking about, which is Tridiagonal, for example. Okay, so we'll have 2 over 4 here, 2 over 4, and below the diagonal we have 1 over 4 and 1 over 4. All remaining items are zeros. Okay, you have a 0 here and 0 here. So you have a matrix which is 3 by 3, as you can see. Okay, so its symbol A theta, frequency response, in fact, is real, and A theta is equal to 1, A of theta is equal to 1 at frequency theta equals 0. So we have what we call a low-pass filter. So the frequency response would give you the following. Would give you half of 1 plus cosine theta, which is always going to be positive. And what it brings, it brings this kind of 3 or 2 ideal filters, as presented in this figure 4.3. So the highest frequency, theta equals pi, produces the infinitely long plus minus signal, which is given by minus 1, 1, minus 1, 1. And that signal has AY equals 0. It is filtered out. And a typical component of AY is given by minus 4 plus half minus 1 over 4 equals 0. And we see this also from the symbol, which is a theta, which is equal to half of 1 plus cosine theta, which is equal to 0 at at theta equals pi. Sorry, this should have theta. And you see the two ideal filters represented. Okay, so in fact, this is the last slide for today. Probably I'll continue with wavelets. Probably not. It depends on the outcome of the application we're going to see, inshallah.